I now want to continue where we left off at the end of the last video. So let me just remind you where we'd got to. We'd proved the following inequality, which I'm actually going to use in a moment, which is the average, where f is some function from defined on a group, taking complex values, average f of x plus d, f of x plus 2d. The modulus of that is less than or equal. Oh, so I had f1, and this is important actually. f2, f3 is less than or equal to the L2 norm of f1 times the U2 norm of f2 times the U2 norm of f3. And just to remind you, the definition of the U2 norm, the definition I'm particularly going to use, it's the average over all x, a, b, but there are several equivalent definitions which I gave last time. F of x minus a, f of x minus b, f of x minus a minus b. And I now want to do something similar for this, except now I'll have four functions. It'll go from x up to x plus 3d. I'll write that down in just a moment. Just before I do that, I want to remind you that we define delta a f of x to be f of x times the complex conjugate of f of x minus a. And I'll extend that notation slightly. I'll write delta ab f of x is just delta a delta b f of x. And so if you work that out in full, that's f of x. Well, it's this thing here. So f of x minus a, f of x minus b, f of x minus a minus b. And we can carry on delta ABC. Actually, I think I'll just write it. I won't bother with the comma. Delta AB, f of x. Will not. There won't be an ambiguity about this being the product or something like that. Actually, come to think of it, I'm not absolutely certain I'm going to use this, but it's nice to have it. And so now let's just dive in. And by the way, I'm not going to state the inequality that we're going to prove. I'm just going to start proving it, and we'll see what we end up proving. I feel that's, in a way, a better way of doing it. It reflects more closely how the result was discovered, which I know because this is actually a result of my own. So it's not what I'm going to show you is a sort of more like a rational reconstruction of how it was discovered rather than exactly how it was discovered, but it gives us it's a similar process, but streamlined. And just before I continue, once we've got this inequality, we can then say that if you've got a set A and its balanced function f equals a minus delta, where delta is the density of A, has a small u, sorry, that should have been a 2 there, has a small u2 norm, then this expression with f1, f2, and f3 all equaling A is very close to delta cubed, which is what you would get for a random set. Okay, so let's dive in then. So we've got an average over all x d, f of x, f1 of x, f2 of x plus d, f3 of x plus 2d, f4 of x plus 3d. And as before, it's quite nice to square that, so let's do so. And then we can apply Cauchy-Schwarz. And to make it clearer how to apply Cauchy-Schwarz, we can just rewrite this very slightly. Let's get rid of that comma. So it's f1 of x, and then I'll stick the e of d in there. The reason that's I said it's obviously the same, but the reason that's a little bit easier to see from the point of view of Cauchy-Schwarz is that now we see that it really is the average over x of one function of x here, and then a rather more complicated function of x here. So that's less than or equal to the average of x, f1 of x squared, times the average of x of average of d f2x plus d f3x plus 2d f4 of x plus 3d squared. And so this first term here is just the square of the L2 norm of f1, and we're interested in the second term here. So let's think about that. So we have, I'll write it out again. And I'm going to use a little slight trick, but it's once given, if you've watched carefully the previous video, this is not a big thing because it's repeating something that we did then. So when I want to expand out a modulus squared, as I said before, if you've got something that you're summing over or taking average over inside, then the way to do it is to take two copies of this variable here, and then you have the function of one variable and then the function of the other variable with a complex conjugate. But instead of calling the other variable d dashed, I'm going to call it d minus c. And so I'm sort of doing that and changing variables at the same time. And it just saves me a little bit of writing just to explain that verbally. So it's the average over d, and see, I did that, as I say, when I was talking about progressions of length 3. I did the same thing, but I did it in 2 steps there. I'm just going to condense those into 1 step now. So I get f2 of x plus d, and then I get f2 of x plus d dashed, but d dashed equals d plus c, or d minus c, I mean, so d minus c bar. Then f3x plus 2d, f3x plus 2d minus 2c bar, and f4x plus 3d, f4x plus 3d minus 3c bar. And now using our nice fancy notation, we can condense that, because that is nothing other than delta c of f2, or partial c f2, evaluated at x plus d. And then the next one is partial 2c of f3 evaluated at x plus 2d. And then partial 3c f4 evaluated at x plus 3d. Now we should get a little bit excited here because we've got a progression of length 3. And in fact, as x and d range uniformly over the group, we have, and by the way, I'm still assuming that the group is not a multiple, has its order is not a multiple of 2 or of 3. So as x and d range over the group, the triple x plus d, x plus 2d, x plus 3d ranges over all arithmetic progressions. So I can actually rewrite that as, I can take the c outside, and then I can write x d delta c f2 of x delta 2c f3 of x plus d delta 3c f4 of x plus 2d. By the way, I seem to have lost a mod sign, but that's because this was guaranteed to be positive because it's a sum of squares, and then I've got equalities all the way, so I don't need the mod sign there. But if it makes you feel more comfortable, you can put it. But at this, well, so that is going to be less than or equal to the average over C. So we have an inequality, which I just reminded you of earlier, up here, that tells you an upper bound for expressions of this kind. So I'm going to apply that with this as my F1, this is my F1, this is my F2, and this is my F3. And so I get delta C F2 L2 norm, delta 2C F3 U2 norm, and delta 3C F4 U2 norm. And now I'm going to apply Cauchy-Schwarz. So that's less than or equal to average overall C delta C F2 2 squared to the half, and then another average over C delta 2 F3 U2 squared delta 3C F4 U2 squared. I'm doing two steps that I could have condensed into one, but because I'm going to apply Cauchy-Schwarz again to this bracket here, so that's less than or equal to average over C. I'll think about these terms in a moment, to the half, and then I get, if I apply Cauchy-Schwarz here, I get delta 2 F3 U2 to the fourth, and now to the half, but then I've also got that to the half there, so to the 1 over 4, and same thing, delta, should probably have been a delta 2C, yes, and now delta 3C F4 U2 to the 4 to the half. So let's now think about what all these terms look like. We've actually basically seen this already, but I think I've got a fresh sheet here actually. So average over C. So what I'm doing now is really quite an easy exercise. So I'm going to do the bit in the brackets without the half power. So that is the average over C of the average over X of delta 2 F2 of X squared. So that's F2X F2X minus C squared, and something's wrong there. Or is it? Let me just do it in two steps. Something didn't look right. Perhaps it was okay, but that's the average over C of the average over X of delta 2C F2 evaluated at X squared. Oh, yes, I think it's fine. Sorry, I don't know why I had this is what I wrote before. I don't know why I had a crisis of confidence just for a brief second. So F2 of X, F2 of X minus 2C bar. That's the value. That's delta 2C of F2 of X, and now I want the complex conjugate. So I'm not quite getting what I was expecting, but maybe that's okay. So when I take the I get this, which equals x and x minus c just range over all pairs x and y, and so I'm ending up with the average of x, f2 of x squared, and then when that is to the half there, that shows me that that bracket is going to equal f2 L2 norm squared. Okay. Now let's have a look at this bracket, which is the more interesting one. So we've got the average over C, and again I will just do the bit inside the bracket, delta 2 F3 U2 to the power 4, and I'll do it in 2 steps, although I've had enough experience that I can in fact do it in 1 without much trouble. That's a delta 2c. And actually, just to simplify things, I'm going to observe that since the group is has order not a multiple of 2, if I actually take the average and put just a delta c there, it's going to be the same, because c ranges over the group exactly the same. Uniformly when 2c ranges over the group uniformly when c does. So I've got this, and so that gives me the average over c, and now I want to take the u2 norm to the 4 of this function here, so I'll take average over x, a and b of delta c f3x, delta c f3 x minus a bar, delta c f3 x minus b bar, delta c f3 x minus a minus b. But now let's have some fun and expand all that out. So that's average over x, a, b and c of I'm going to put first of all the terms that don't involve c. So that gets me f3 of x, then I'll have an f3 x minus a bar, and then an f3 x minus b bar, and an f3 x minus a minus b. And now I'm going to put in the ones that do involve c, and so that gives me f3 x minus c, but with a bar over it. And here I'll have f3 of x minus a minus c without a bar, because I've taken a bar twice. f3 x minus b minus c without a bar, and finally f3 of x minus a minus b minus c with a bar. And you see that it's awfully like the definition of the u2 norm, but just generalized. So instead of just 2 variables together with the x, we have 3 variables together with the x. But again, we take all possible choices of, all subsets of a, b and c to subtract. And when we subtract an odd number, we put a complex conjugate, and when we subtract an even number, we don't. And so this thing here we call the u3 norm of f3 raised to the power 8. It's not quite as obvious as it was in the case of the u2 norm that the f3 norm is a norm. And that's something we'll talk about. But for now, we just note that we have shown that this is at most the f3 norm to the 8 to the quarter. So that's f3 u3 squared. And then this thing here, again, using the fact that 3c ranges over the whole group when c ranges over the whole group, is equal to f4 u3 squared. And because I squared right at the beginning, it turns out that the inequality we've proved is that the average of xd f of x plus d, f1 of x, f2 of x plus d, f3 of x plus 2d, f4 x plus 3d is less than or equal to L2 norm of f1 times the L2 norm of f2 times the U3 norm of f3 times the U3 norm of f4. My hesitation was that U3 norm of f4. I thought I was going to get the U2 norm here rather than the L2 norm. But I think I made a mistake in the notes which needs correcting. But what really matters is that if one of the U3 norms over here is small, then we have an expression that's small. And to see why that really matters, let's go on and, so here I've defined the U3 norm. By the way, you can guess what the UK norm is now. Once you've got the U2 norm, it's with this, the U3 norm is this, and of course the U4 norm, I'll add in a D and take all possible combinations there with appropriate conjugates and so on. You can also guess that by generalizing this proof, you can get that an inequality similar to this one with f1 up to fk and the UK minus 1 norm coming out. But and it might be worth doing. I'm not sure I want to set it as an exercise on the example sheet, but as a sort of exercise to check your understanding and your ability to do the manipulations. Might be quite a nice thing to do. It'll be an obvious induction in the same way that this was deduced from the U2 case. But let's now have a look at, so let A be a set of density delta, and let f be the balanced function. I would like to get a bound for or an estimate for average over all x and d of ax plus d, ax plus 2d, ax plus 3d. And in particular, what I want to prove is that if this balanced function has a small u3 norm, which will be my, informally I think of that as A being a bit like a random set of density delta, then I want to show that this quantity is going to be approximately equal to delta cubed. So that's the delta to the fourth, I mean. That's the thing that we're going to be trying to prove. But let's just see what it actually equals. So as before, I just expand, I write it in this form. And now, whereas before I had a sum of 8 terms, now I've got a sum of 16 terms. And let's just think about how those work. So if, so I better write this. We have a sum of 16 terms. Maybe I could call it a sum of 16 sums. So, but each term is itself an expectation. So we have a sum of 16 terms. So the main term, that's where you choose delta out of each bracket, is delta to the fourth. And we want to show that everything else is small under suitable assumptions on f. If we choose 1f, we get zero, because f average is 0. And if we choose 2 f's, we also get 0 because, for example, and again this uses the fact that the group doesn't have its order isn't a multiple of 2 or 3. So then something like a pair x plus 2d for random x and d is uniformly distributed over the whole group, and therefore the average you get delta squared f of x plus 2d will be 0. If we choose 3 f's, then at least one of them is in the last 2 brackets. So if we choose 3 f's, then well, I'm not going to be too fussed about the precise bound. We get at least one contribution of fu3, and everything else is certainly at most 1, because f takes values in -1, 1, and it's easy to check that therefore all these norms are at most 1. So then we get at most f u3, and in fact that also applies if we get 4 f's, we get at most fu3. And so we get an upper bound of fu3. Now, that's not quite as good as in the u2 case. We got a bound of f of u2 squared, which was quite nice. But that was because if you chose 2, then you couldn't. But sorry, there are 4 ways of getting 3, so I need a constant 5 in front of that. Because the sort of n-1 case, so in the case of progressions of length 3, it was the 2 case, you got 0 automatically, whereas here when you've got 3 things, you don't get 0 automatically. Although if you work a little bit harder, you can in fact improve that to a squared, and I'll just sketch how you do it. The rough idea is that you can copy the argument that I've given here and to move these u3s around, so you can choose which 2 are the L2 norms and which 2 are the u3 norms. And so then if you do that, this can be improved to a squared there, but I don't mind about that too much. I'm going to stick with this upper bound here. That I might put as an exercise. So that's the main message that we've got here. So the corollary is then that if a minus delta u3 is less than or equal to c, then the average of ax plus d, ax plus 2d, ax plus 3d minus delta to the 4th is less than or equal to 5c. So if c is significantly smaller than delta to the 4th, we find that A will certainly contain an arithmetic progression of length 4. So once we've got to that point, what is the task, which I'm not going to start on yet, but in the next video I will. What's the task ahead of us? It's to say if, so A minus delta equals F, if F u3 is greater than C, what can we say? So we know that if fu2 is greater than c, we've got a large Fourier coefficient. Now the u3 norm is bigger than the u2 norm, so the statement that fu3 is greater than c is a weaker statement. I haven't actually proved that the U3 norm is bigger than the U2 norm, but that again is an exercise which I think I will put on an example sheet. So because this norm is bigger, this is a weaker statement, which means it's harder to deduce anything from the fact that the U3 norm is large. And what we're going to find is that if the U3 norm is large, we got some kind of quadratic structure associated with the function f. But that's a treat for later in the course. And there I will stop this video.